Hello and welcome to chapter 16, which is on mirrors and lenses. So I'm just going to get started. So mirrors and lenses are actually something that we've known about since Newton's time. This is what Newton was actually interested in, more so than he was in mechanics. He spent his entire life trying to come up with a theory of optics, which is the theory of how light interacts with matter. So the what we're going to do is we're going to start with the type of uh, light that Newton liked to work with, the type of model that Newton worked with, which is light as a ray rather than a wave. Uh, so this is called geometric optics, where light is uh, modeled as traveling in a straight line called a ray. So if you've taken a mathematics class, you'll probably remember that a ray is a straight line that comes out from a source and has a direction. So, for example, if we have the sun, like I'm drawing here, we can have all of these rays of light coming out of the sun, and we can just treat them as straight lines that are coming out the sun. And then this is pretty much the accepted way to do it when we're talking about this classical sort of optics and this Newtonian sort of optics. So when light interacts with an object several times larger than its wavelength, it acts more like a wave than a ray than a wave. And then this is called geometric optics. So in this chapter, we're going to focus on two laws that govern how light changes the directions when it interacts with matter. The law of reflections for situations in which light bounces off of matter, and the law of refraction for situations in which light passes through matter. And just a moment. There we go. So reflection is something that should be fairly obvious, is just when a ray of light bounces off an object. The law of reflection says that the incident ray is going to be at the same angle with respect to the normal, which is the line perpendicular to the surface, as the angle of reflection. So the incident and reflected ray both come out, or sorry, yeah, they both come at this go in and come out at the same angle, where they don't even go into the surface, they just bounce off the surface. And then the reason that most objects that we see, this isn't immediately obvious. So you can see like a page in a book from any given uh, with light bouncing off of it from any given angle instead of just a specific angle like you might be able to with a mirror, because which is because most objects are really messy and uh, rough. So if you look in the second or on the bottom right hand corner, you'll see a diagram showing what happens when the rays hit a rough object. They're still going to be reflected at the same angle as the angle of incidence. It's just that what is the normal, what's line points perpendicularly out of the surface, is changing so much over the course of the object that it just kind of scatters around, and this is called diffuse light. So another thing that we want to define is a real versus virtual image. So a real image is an image when light appears to come from a place where it actually passed through. while a virtual image, such as a reflection from a mirror, is when light is reflected or refracted. We're going to get in to what refraction is in just a moment, in such a way that it appears to come from somewhere else. So when you look into a mirror, you're going to see an image that appears to come from behind the mirror rather than in front of it, even though none of the light actually came from the place where the image is. The light just reflected off the mirror and into your eyes. So this is the basics of how mirrors work. And then what we do instead or what we do kind of to make them more useful and practicable in physics is we make spherical or parabolic mirrors. So parabolic is the shape that we were talking about when we were talking about uh, motion with acceleration due to gravity, which is just a shape according to, there we go, there's my pin. It's the shape that just goes up according to x squared. But these are pretty hard to make, so what we instead tend to do is make a spherical mirror, which is a mirror that is part of a sphere, but since we don't go all the way around the sphere, it becomes pretty close to what you would see with a parabolic mirror. So it's pretty close. So that's the difference between parabolic and spherical mirrors. I'll use the terms interchangeably, but they are technically different things. And one of the problems, or one of the properties rather, of parabolas is that if you shine a ray of light straight down parallel to the central axis, where the central axis is just this line that the parabola is, or if it's 3D, it's going to be a hyperbola, technically. That's just some more me being specific to avoid giving you bad information, but it's still pretty fairly, or it's still pretty fairly accurate. So a parabola, when you go through this central axis, when you have a line that's parallel to it, it will reflect the ray, no matter where it comes from, into a point called the focus of the ray, which is somewhere along the central axis. So you come from this end, it's going to go through the focus. You come from the other end, it's going to come through the focus. All of these light rays go through the focus of light, or go through the focus of the parabola, or the hyperbola, or the sphere. And that allows us to use them to reliably make images that are different sizes than the initial image that you saw, like you would see out of a flat mirror. So for a convex mirror, which is the mirror that you see on figure B, figure B on the bottom left-hand corner, the focus is actually behind the mirror, and it's scattered so that, and the light is scattered away from that focus, so that it looks like the light came from the focus behind the mirror, when in reality, this light never passed through the mirror, or it never passed from behind the mirror. It's just reflecting outwards at bigger angles than it came in. So it can create a virtual image. As you see in figure C of the bottom or of the right-hand figure, it creates a virtual image where it looks like there is if you place a candle in front of the mirror, it looks like there's going to be a candle, all the light is coming from a candle behind the mirror because of the way the mirror is shaped. It scatters the light out so that it looks like it looks like the light's coming from behind the mirror, but again, it can't. And then you also have the concave mirror, which has a focus in front of the mirror, and can create real images, which if you look at figure A on the right-hand side, if you have a object farther away than the focal point, then it reflects the light coming in, and the light that comes in actually passes through this point where it looks like the mirror, or where it looks like the image is coming from. And then if you have a concave mirror, it can also create, or first of all, if you have the concave mirror with the real image, it's going to flip around like you see. It's a little hard to see in this drawing, but at this point, the candle is pointed upside down. Whereas if you put the focus inside of the focal point, or you put the object inside of the focal point, so closer to the mirror than where all the light scatters, then it's going to create a virtual image that's going to be bigger than the initial image. So the basic rules are that a concave mirror, if you're farther away from the focal point than if your object is farther away than the focal point, will create a real image that's flipped upside down. If you're closer to the mirror than the focal point is, then we'll create a virtual image, which again is just an image where it looks like it came from behind the mirror, when really none of the light could have passed behind the mirror. It's all reflected off. So that's what's called a virtual image. And that is going to give you a virtual image that's bigger than the initial object. And then the convex mirror is always going to give you a virtual image that is smaller than the object. Or, yeah, yeah. Yeah, it's always going to give you a virtual image. As I say this, I'm not 100% sure about it being smaller than the object, but I think with the reasoning that I'm using right now, it should be. So way that you can test this out is you'll see these at convenience stores, right? You'll see a convex mirror or a convex mirror at a convenience store, like we see in this first drawing on the upper left-hand corner. And then, or not drawing, just it's actually just a picture in the upper left-hand corner, where they want to use a convex mirror because it makes everything look smaller than it is, which means that you can see more of the convenience store, more of the store through the mirror than you would be if you just had a straight mirror or just a plain mirror, like you might see. I have one right now, but I'm not going to get that out. Just like a plain mirror that you'll see in a bathroom. And then another use of the spherical or parabolic mirrors is the car headlight, where a headlight is placed at the center of a parabolic mirror, which is just going to reflect all of the light out and directly in front of you. So it's placed in the center of the mirror so that all the light that comes out is going to be reflected. That's reflected by the mirror is going to form a beam going straight in front of you while you're driving your car. And then another and probably the most scientific use of this is current telescopes, which instead of using lenses, which we're going to get into in a little bit, use reflecting parabolic mirrors so that you have most of the light coming in and it hitting a large parabolic mirror, which is then reflects the light onto a smaller mirror in the center, which is able to reflect it straight into your eye or straight into the detector or whatever you're using. So on this XKCD comic that isn't from the textbook, but I still decided to use, you have all the benefits to or using mirrors instead of lenses, where lenses are more expensive, less compact. There's something called chromatic aberration, which is caused by the fact that the lenses aren't strictly parabolas at all, or aren't strictly parabolas either, and also different wavelengths of light pass through mediums at different angles. And then it also doesn't allow you to make as much, or it doesn't allow you to gather as much light because all of the light has to be passed through the lens, and then it's just yeah, it doesn't allow you to gather as much light because not as much of the telescope is being used to gather light, as we can see in the difference between the refractor and the reflector in this drawing. So these are just really useful, and then even though we haven't gone to refraction yet, so we don't actually know what's happening there, those were the first types of telescopes. And we eventually just took them out. We eventually replaced them with reflector telescopes for the most part. So refraction is what happens when light actually passes through a medium. So when light passes through glass, it bends a little bit, which you can tell if you're looking through into a swimming pool or something. The bottom of the pool always looks a lot closer to us than it actually is, because the light is actually bending and making it look farther, or making it look closer as we look at it. So I'm just going to read out what I said. So as light passes from one medium to another, its speed changes. Because of this changes the wavelength of the light, It also changes the angle at which the ray of light moves through the new medium. This peak of each wave has to be the same on both sides. This change from one medium to the other is called refraction. So what I mean, so if the speed of light changes, then because lambda times frequency is equal to speed, frequency can't change because that's just how often a peak comes by. And as you look at the interface between the two objects, a peak should come by at the same rate, no matter if you're looking at one end or the other, because it just makes sense that if you have, say, a wave of water, then the peak of the water as it goes from salt, say like a salt water to a clean water interface, or to a non-salt water interface, then the peak of every wave is always going to be coming just as often. It's just that the velocity of the wave as it passes through is going to change. So to demonstrate this, I'm going to use something called plane waves, which are basically just drawings where each line represents the peak of a wave, or it represents the peak of a wave. Yeah, like I said, it just represents the peak of the wave. So these come once every period, and period is the inverse of frequency, so period's related to frequency. But because they go through different, because they have different speeds, they have to have different wavelengths. So the wavelength is going to be the distance between each of these peaks. So this is one wavelength of your initial wavelength, and then this is your second wavelength, which I'm going to call lambda prime. So it's kind of hard to tell, but the wavelength of the second one is smaller, but it has the same frequency. So in order for it to occur, these peaks have to occur on the same spot at the interface, whether you're looking at the wave that's coming in or the wave that's going out. So in order for it to go through, it has to go through at a different angle, like this. So this distance is constant. This distance, lambda, the distance between peaks, is different. Therefore, this is kind of an opaque, or it's kind of one of those things that takes a little bit to get through, which is why I don't think they explain it in the book, or it takes a little bit of thought to get I understand, because the distance between peaks has to be the same, or the distance between peaks of each wave front has to be the same, but the difference in peaks as it travels. So the distance in peaks along the interface has to be the same, but the distance in peaks as it travels through the interface changes. That also changes the angle that it passes through. So if we went out again, we would see this wavelength, and then this one has to be going at a much more severe angle. So this is determined by the index of refraction n, which is defined as n is the speed of light in a vacuum over the speed of light in a medium, which is going, which just tells you how light travels through the medium. It just tells you the speed of light. And because of the wavelength is dependent on velocity, and then this angle is dependent on wavelength, this angle is also dependent on n, which is the index of refraction, which is dependent on the material and the wavelength / frequency of the light going through the material. So this relationship between light and refraction, which refraction is just the passage of light through the passage and bending of light through a material, is given by something called Snell's law, where n1, the index of refraction times the sine of the angle that it makes with respect to the normal is equal to n2, the index of refraction of the second medium times the sine of the angle that it makes with respect to the second medium. And then one great way to see this is just to shine light through a prism. So if you shine light through a prism, you're going to see that the wavelength, you're going to see that the instant light is going to be a ray which goes at some angle with respect to the normal, theta. So this would be theta1, and then this angle would be theta2. And this angle is smaller than that angle, which is something that comes out of Snell's law. And then comes out the other side at a different angle, which is also dependent on Snell's law. But if you take, that's true if you just have one wavelength. But something that happens is that index of refraction is actually dependent on the frequency of the light that you're looking at. So if you have instant white light, which is light that's made up of every different color, and you pass it through a prism like this, it's actually going to spread all of the light out, because the angle that the each wavelength makes with respect to the angle that each angle makes with respect to the normal inside the prism is going to be different. So when it comes out, it's going to be spread out in into a rainbow. So what actually happens with rainbows is that sunlight passes through a water droplet, and the water droplet and in the water droplet, different indices of refraction are available for each of the different colors. So red, orange, yellow, green, blue, indigo, and violet. And then all of those wavelengths are going to spread out. And I didn't mean to imply that the only colors were the colors of the rainbow. It's just that those are the colors that we're best at seeing. So that's tends to be why it's broken up into bands, when really it should, if we could see every color as well as possible, as well as we saw any other color, it would just be a gradient from red to violet. And then the next thing that I want to talk about with Snell's law is total internal reflection, where an instant ray goes from some it goes from some n1 with a, I believe, higher index of refraction to some material with N2 a lower index of refraction, and then the reflected ray or the refracted ray is going to come out at an angle greater than the initial angle, the instant angle that it passed through the medium from N1 to N2. And then what you can actually do is you can make it so that the light that's refracted would only come out parallel to the surface at theta 2 equals 90 degrees. At that point, none of the light is actually coming out of the material. Or, yeah, it's not coming out of the material, it's just grazing along the side. And then this is called theta critical, the critical angle, where I'm sure I've said this somewhere, but theta is just generally the variable that we use for angle. And then if you have any angle greater than theta critical, then none of the light is going to pass through, and it's called total internal reflection. And then I'm doing a few drawings this one, but it takes a little while to clear my board, so sorry about that. And then you see some applications of this. So the critical angle of a diamond, if it's cut, or the diamond or of a diamond is pretty low. So if light passes through a diamond, hits another facet of the diamond so that it is hitting the air at an angle greater than the critical angle, then it's just going to reflect out, and it's going to keep reflecting out until it bounces, or it's not reflecting out, it's reflecting back inside the diamond. It's going to keep reflecting back on the insides of the diamond unless it hits it at some very specific angle, which is why diamonds seem to shine. And then another example of the use of critical angles is just using binoculars. You have two prisms which they reflect inside. Light comes in through one prism, it reflects to the side, it reflects down, it reflects to the side, and it reflects up, so that even though your eyepiece is looking directly at something that's just the inside of the binoculars, you're able to see what came out through, or you're able to see through the lens of the binoculars through the wider set edge through this total internal reflection. And then the last application I want to bring up for this is just fiber optics, where you have a material of some refractive index, and you want it to always be the light to always be inside of the material, to not like just shine through the material and then come out the other side. So you want it to go and almost always be at that critical angle. So you set up the material that you want to pass through, and then you set up an outside coating, which makes it so that the critical angle is very, very, very hard not to make. And then if you do this, then it's just going to keep internally reflecting over and over as it passes through the fiber optic. And that allows us to transmit information at the speed of light in that material. So the last of these 3 sections that we're going through, this chapter really could have been 3 chapters. So I am skimping a little bit on the details, but hopefully you'll forgive me for that. Is convex and concave lenses, where there are lenses which are set up to either bend light towards a focal point on the other side of the lens, like we saw with mirrors. So they are just basically parabolas or spheres as well. It's just that, yeah, it's just that when you have a convex lens, it does actually pass through a focal point. Whereas when you have a concave lens, it bends light away and makes it look like the light is coming from a focal point, even though it never actually passes through that focal point. And in that case, you're going to get virtual images. While for a convex lens, a lot of the time you're going to get real images. And yeah, these are useful, but a problem with them is that they have to be really thin. And if they aren't thin, then with what we said about the prisms, where the prisms would break light into different colors, these lenses will also break light into different colors and have different focal lengths for different colors. And the thicker they are, the more noticeable this is. So that is why the telescopes don't generally use these types of lenses anymore. They usually use the mirrors. So there are different types of cases where F is positive is a convex mirror, and the distance that you are farther away are from the mirror, not convex mirror, convex lens, and the distance that you're away from the lens is greater than F, then you're going to get a real image, which means that it's going to be something that actually passes through the point that it looks like it passes through, but it's does but it's going to be smaller, and it's going to be flipped around. If the distance from the lens is less than F, the focal length, then you're going to have a negative distance of the image, which means that it's going to look like it's closer to, or it looks like it's coming from the left side, if we take our image to be from the left side, and then, or if we take our object to be from the left side and the lens to be pointing towards the right, with a positive magnification, which means that it has a greater value, or it looks bigger than it actually the object really is. And then case 3 is a negative f, which is the state that it's the rule for concave lenses, which is going to give you a virtual image and with magnification less than 1, so it's going to look smaller than it actually is. So that's basically it for like how lenses work, but I realized that I've been kind of dancing around the idea of what an image is. So one way to do that is to do ray tracing for lenses. So you know that any light that passes through a lens that's parallel to the axis, the central axis of the lens, like we were saying with the mirrors, is going to bend towards the focus. So right now we're only talking about convex mirrors instead of convex lenses instead of convex mirror, concave lenses. So you know this first case, any light that comes out of your image that's parallel to the central axis is going to bend towards the focus. You also know that anything that goes straight through the mirror, straight through the center of the mirror, is not going to bend at all. And anything that goes through a focal point on the left side of the, I keep saying mirrors when I mean lenses. We're talking about lenses right now. We're not talking about mirrors. I hope that really doesn't confuse you. But you have light that's going through the focal point, and then that's going to be straightened out so that it's parallel to the so that's parallel to the axis of symmetry to the central axis of the lens. So that straightens out for the same reason that but opposite, that the lens, the one parallel that's initially parallel to the axis is going to go through the focal point on the other side. Anything that goes through the focal point on this side is going to be straightened out because it's basically just undoing what you had done earlier. And what that means is that you have these 3 rays, you know where they're going to go, and you know that these 3 rays have to happen. There's a really close to infinite number of rays that could be coming out of you, so you have to have at least 3 rays that you know are going to happen, and you know what's going to occur when they do pass through. And from there, from overlapping these 3 rays, you'll see that they all converge on a point, which is a distance di away from the lens. So this is talking about like very basic ray tracing, but they all converge on that point and then start moving away from that point. So what it looks like is that they started out at that point and then released the light, and then the image released the light from that point instead of the image actually releasing the light from the initial object, because you're bending all these rays, because you're messing around with the distance and because you're messing around with the rays of light that are coming out. It looks like they all came from this point, which means that to an observer, they will, to whoever's looking at the object past the lens, it will look like they all came from the point of the image rather than from the point of the object. And that's what I mean by images, and that's what's meant by real and imaginary images. So you can see that the concave lenses are always going to be imaginary lenses because it looks like the light is coming out from, instead of being some distance away on the left side of the axis, it looks like the light is coming from another object some distance away from on the left side of the axis, even though the light rays never actually pass through there. They only pass through, they only get bent so that it looks like they came through there, and that's going to be a virtual image. And then, yeah, I believe the final thing that I want to talk about is just like microscopes and telescopes, where you have two lenses in order to really control where you're looking at and really control the magnification, which is how much bigger it appears. And then what you do is you adjust the distance between the lenses so that one object, or well, first of all, light passes from an initial object, which is H on this left-handed or on this left diagram. It passes through and it creates an image that's going to be on the right side of the object or on the left side of the object or what have you. It depends on how you it depends on how you're looking at it. And it passed that image, the rays that come from that image pass through the second eyepiece, where the first lens is called the objective, the second is called the eyepiece, and creates a third image on your in your eye, in the sensing apparatus and whatever, so that it looks like the object is actually coming from either significantly closer or significantly farther away. So basically, what microscopes and telescopes both do is they create very, they allow us to really control where an image is by letting us choose the distance between the eyepiece and or distance between the eyepiece and the objective lens, which is going to allow us to control what it looks like the image is. And for a telescope, it allows it to appear yeah, both with telescopes and microscopes, it allows it to appear much larger than it really is. So this was initially developed by Galileo. So we knew a lot about light even before Newton, because Newton came after Galileo. But Newton was the one who really did the work on prisms and breaking light into its component forces. And then, in addition to like the obvious applications that we have here, we also have we also have eyes. And eyes are basically just lenses. it goes into detail about this in the book, but it was a few or 3 or 4 pages, and I didn't want to make this any longer than it was already going to be. But if you want me to, I can upload another video just explaining how the eyes work as given in the book, which is more of a biological apparatus than we see, but it does run on the same physics of lenses and reflection or and refraction. So I hope that that was all very interesting and good for you, and I will see you later.